On our Earth's dynamic surface, rocks are continually being stretched, compressed, folded, and faulted. We will see that giant layers and formations of rock rise from thousands of feet under the ground to lofty heights in the tops of mountains. Together, we will enjoy the amazing beauty that folded and eroded rocks offer us. Why, hello there. Here I am along the beautiful Gallatin River. It's southwest of Bozeman, Montana, and it cuts through a spectacular mountain here. I highly recommend this drive from Bozeman to West Yellowstone, Montana. It's spectacular, right along Yellowstone Park. But I come here for a very specific reason, and that is to start this episode, this video that I'm doing on structural geology. Now, structural geology is the study of how the earth is deformed, how it gets squished and broken and all that kind of, the faults like the famous San Andreas fault in California and others, etc. But I wanted to introduce you to some basic concepts to this folding. And this rock we're looking at is 2.5 billion years old. It's the oldest rock in the continent, like Wyoming. There's this fairly small core area, and it has been buried at least 12 miles deep. It was at one time under high pressure and heat, which allowed the rock to deform dramatically and form what we call metamorphic rocks, meaning they've been cooked up, not quite melted, and they're often deformed, and new crystal minerals and stuff, beautiful minerals, can grow in metamorphic rocks. So we're going to look at these rocks here at Gallatin Canyon and see some of these folds. They're really cool. So here I have my sketchboard. Point one, very important when we're looking at deformed rocks that you can think about when you see things in your area where you live. That is, rocks are deposited horizontally. So they're deposited like this, layer after layer after layer. Through time, right? I put an arrow of time, through time, up, up, up. Sometimes erosion occurs and all that, but I won't get into that. Let me put my famous tree here so we understand the look we're looking at. Here's a little tree. We're looking sideways, the layers of the earth deposited horizontally through time. That has important repercussions for you when you're seeing things, because if you see rock that's tipped like this, okay, let me put the ground here. You see rocks that could be tipped up, maybe gently. These are steep. Let me put my tree here. Then you know, wow, something happened here. There was a mountain that was formed or something, because they were horizontal, now they're this way. Or if you see folds, and I'll put some wrinkles in the earth. Okay, I'll put a layer here of rock. Well, now it's pretty obvious, isn't it? Things are getting deformed. And we're going to look at some folds that are literally kind of at this kind of scale, small scale folds, and that's why I'm bringing you here to see some of these beautiful smaller folds, so you have this in your, in your mind, how folding can go from very small to very large. Hopefully not too many cars go by. But look at this wall. Just look at this wall of folded rock. As you examine the outcrop more closely, the more you see. There are tiny little folds everywhere. The whole outcrop is full of these beautiful folds. So this rock was buried, as I said, so deep and under so much pressure, it could fold real tight. Well, this is sure a noisy place on the highway, but let's try this. Wow. My wife, Merlane, found this boulder here. Woo! Take a look at the folded rock in this, would you? Just follow this with me, with my finger folded back and forth like spaghetti. This is very quartz rich and feldspar rich. So just back and forth all down this boulder. You never know what you're going to find out, you know, when you get out and just start looking. It's sure fun.
We've seen some small folds, but they can be much, much smaller. This microscopic image shows a fold that is just 1/10 of an inch across. Crazy.
Here we are back in Wyoming. We're at a big fold. It's called Sheep Mountain Anticline, north of Grable, Wyoming, in the Bighorn Basin. This is where this canyon you see out here is where the Bighorn River cuts through Sheep Mountain Anticline, they call it. And this is a well-known structure in the geologic circles. In fact, nearly every textbook, the introductory textbook to structural geology and stuff, shows you Sheep Mountain Anticline because it's so spectacular to see all these rock layers and how they're banded and the ridges and things that go around this fold, which you'll be seeing here. And I'm excited to show this to you, and hopefully it'll be eye-opening. So let's go to the north end of the fold and find our way there to have further discussion. Hi, I'm way out here. Hope you can see me. This is a very interesting spot to be on a structural fold, a nice folded anticline that we call, and I'll get into more details in a minute here on this. But the rock here, as you can see, the layers in the rock are tipping up and going up into the sky, right? And have been eroded off, of course. These beds are coming around a corner. Look at this. It's like a racetrack. I'm turning. Look how I'm just turning around the corner. Around we go, right around a point. And it turns out that right here is what we call the axis of a fold, right in this area. And it's right at the center of the fold.
Isn't this interesting and kind of strange that these layers of rocks just bend around this corner, a really tight bend on this very large structure that we're looking at? We'll learn more about how that happens in a minute.
I want to explain some of the terminology we use to help us here. That is how geologists, what they call folds, different types of fold. When the fold is this way, kind of like a tent, we call it an anticline. And on the maps, we draw symbols so we can tell what we think is an anticline or a syncline. We'll draw a line down the axis, like that, right down that fold, okay? And we'll have arrows that point down the slope on each side. So in map view, flying like a bird, that's what we see on the symbols. The syncline is the opposite. It's like a trough like this, and we draw a line right down the middle of that with arrows pointing down to the line, to the axis. So that's the symbology for a syncline, and that's the symbology for an anticline. And those are the two significant types of folds that we name. So hopefully that'll be helpful as we go forward. I want to explain another very important concept, and to help with this, I've built a clay model with layers of rock that are folded, and it's kind of in the shape of the top of my head here, and there are different layers within it. Now if we cut this, like erosion, it's often like a knife. Okay, when we cut it, kaboom. We see these beautiful concentric layers like an onion within it, with the oldest rock in the middle in this case, getting younger to the outside because it's folded like an anticline. And these layers can form ridges because they could be resistant to erosion. If you'll watch my video on erosion, this will help you understand that. Or there could be valleys in the shapes of these colored layers here that I have in this model in real life, because they're soft and they erode deeper. So you'll see some beautiful ridges and valleys when we fly the drone and you get a look at the Sheep Mountain Anticline. I want to show you something else here with my clay models. It turns out that when you have folds like this, so, you know, an anticline, a syncline, and then an anticline, well, they're not always horizontal like this, right? They can dip into the ground. We call it plunge. And it turns out that Sheep Mountain Anticline, this fold here, plunges towards the cameras to the north. Now, if it also does to the south on the other end, by the way. But if we take erosion and cut it now because it's dipping into the ground, it does something different. Let's look at that. So now it's dipping into the ground. We've cut it. And if you fly above it, you're going to see beautiful wavy lines, or often they can be really kind of sharp pointed like an M or a W. Depending on if you're on a plunging anticline, they'll bend like this. A plunging syncline, they'll come back this way. And so you'll see some beautiful ridges and valleys in shapes like this. So I hope you enjoy that and it helps you think about that as we see this beautiful fold from the air.
Let's fly up and take a look at this magnificent structure. Notice the Jeep right here. That's a great thing to use for scale. It is a huge structure. We're now looking straight down the axis of the Sheep Mountain Anticline, looking south. And notice the beautiful ridges and valleys along the flanks of this great fold. In fact, if you look to the right side of this frame, way out in the distance, you can see some ridges. And they went up and over the fold and have been eroded off. Can you see the Jeep? It's this tiny little dot right here. And this is the corner where I walked around the axis earlier. And here you can clearly see the axis of this fold along this dashed line. This beautiful, very light pink, almost white ridge we see is the Jurassic Age Gypsum Spring Formation. And it's about 200 million years old, you know, and we know the Jurassic for the age of the dinosaurs, don't we? And it's made of gypsum primarily. Very interesting. We use that, that material to build in houses. Remember, at one time, this was one continual layer that went up and over the fold, right? And erosion acted almost like a knife and cut it off. This is another good place to talk about this differential erosion that I have mentioned in my prior video on erosion. This high area that we see here, the beautiful mountain part of this structure, is capped by the Phosphoria Formation, which is Permian age and is about 300 million years old. And it's very resistant limestone, and the other formations underneath are very resistant. Most of them are very resistant to erosion. Therefore, the erosional process has a hard time cutting through that rock, and it's left up high. Now, through time, of course, it will erode as well.
Here I am on the western flank of the Bighorn Mountains. Now this structure is much bigger than the Sheep Mountain Anticline that we recently saw. That anticline or fold is about 2 miles across and 16 miles long or so, Whereas the Bighorn Mountains here are 35 miles across or so and 160 miles long, the structure, so much, much bigger. And we're observing the beautiful flank in these very steeply dipping layers. In fact, some of them look like they're overturned over there, just slightly overturned. So I want to talk a little bit more about folds and how we're going to relate it to the Bighorn Mountains here. Here I am with my drawing board. I wanted to go through a couple things here structurally that apply in particular to this flank of the Bighorn Mountains in this area, this western flank here, okay? If we take a fold and start, or a layer of rock, right, and start squeezing it, squeezing that layer of rock, it's going to start to fold like that, okay? And the forces I'll put like this, squeezing together, okay? It's going to start that way. And then as you continue to compress, now usually what'll happen is now it'll be a little more steep like that, okay? So I wanted to jump in here real quick and show you a simpler part of the Bighorn Mountain structure where you have a fairly simple fold and it's very obvious to see. Sometimes all we see are the vertical beds in this area and we don't see the nice bending over like we do here. So I wanted to show you this to get you a real clear image before we step into more complicated things. In an area here where it's not faulted much at all and it's a fairly simple fold. Now one thing I do want you to keep in mind is that these big limestone layers that we see that come up over here, there's some 7,000-8,000 feet and higher in places in the Bighorn Mountain, much higher. Down in the basin here, they're 20,000 feet below the ground. So it's an amazing amount of vertical relief, what we call structural vertical relief.
What a beautiful view of the giant fold that created the Bighorn Mountains. Every time I witness spectacular geology like this, I'm struck with awe. This mountain took over 10 million years to form, and these big layers of limestone were deposited in clear, warm ocean waters some 400 million years ago. In fact, I have found beautiful heads of corals and other warm water fossils on the top of the mountain in these very layers. Okay, it's time to jump back to where we were 15 miles to the north and continue our discussion.
And continue. So it went from here, step 1, to this, step 2. And now you're getting really steep on this flank like we are here. Okay? And then the final step in this one here is it's very similar to this. You take a fold, you have a big turn like this, and then you put a big fault. It breaks, the rock breaks like this. There's a fault here. Okay, and I'll put an arrow here showing up, this side's up. So the layer of rock comes here and it breaks and then it continues down underneath like this. Something we'll say like that. So it was here like this, pretty continuous. And then of course it just can't handle it and it breaks, but it continues to push. And now you have this big fault. This layer of rock is faulted up from here to here. And you can have tremendous amounts of throw, we call it, or displacement on that fault. You can have thousands of feet of displacement on this fault. So what we're looking at here is a situation kind of like this. Is the beds on this side of the Bighorn Mountains, the layers of rock right here, are vertical or even overturned. They've even been bent over backwards. Okay? And so we're standing here looking at the front of the Bighorn Mountains where the layers of rock are like this. They're vertical and they're bending around, okay, like this. We're looking at this area here. So we're going to see these vertical rocks. And they go up and they don't come back down on the other side of the mountain for 35 miles. So, of course, as these rocks are folded, let me put a few more layers in here, okay? I'll put a big layer here, like this. I'll put it over here like this. So this layer here of rock. These layers, and then there are more layers and etc. Okay? So these are the rocks that are folded. But remember, what we're observing is what's happened after erosion. So as the mountain is being uplifted in this big fault, things are being thrust up. It's being eroded continually. And what we see is what it looks like, well, present day, where there's been thousands of feet. We're talking 15,000 feet of erosion off the top, clear down into the core. So let me do that. Let me just, for the heck of it, I'll put my finger here and erode, down here. And here will be the mountain, the Bighorn Mountains here, like this. Let me put the surface of the mountain, something like this. So we have the mountain that's been eroded. And so we're seeing these vertical layers in here that are vertical and have been eroded off. Let me put another layer in here. It's getting a little messy, but the erosion has cut those off and we're looking at them, okay? And out here, not very far in front of the mountain, you can't see it, but right out here, I'm looking at layers of rock that are horizontal right out here.
So as we take this Google Earth image and rotate it to look to the south, right along the Bighorn Mountains, now you're going to see these red lines that I've drawn, these dashed red lines. Those represent the thick sedimentary layers of rock, the formations of rock that went up and over the Bighorns and were eroded. In fact, I could draw more lines up above those. It's just I drew a few to represent it. And remember, up to 15,000 feet of these sedimentary rocks and even basement rocks were eroded off the top of the Bighorns. Amazing to think about.
So hopefully with this discussion on erosion, okay, and the folding and how layers get vertical and faults and all that, you'll have a much better understanding of what you're looking at. And hopefully that helps.
Okay, let's fly back away from me and notice these nearly vertical red rock layers named the Chugwater Formation and how they have been very sharply eroded. It's hard to believe that this formation at one time went up and over the mountains. As we continue to back away, we see giant fins of limestone and dolomite pointing skyward. These layers plunge nearly straight down into the earth for some 20,000 feet. That's nearly 4 miles. The rocks in this area are crystalline basement, which is some 2.5 billion years old. And some 10,000 feet of sedimentary formations have been eroded off the top of the mountain down to this basement. Hard to believe.
So now that we've had this discussion, I want to show you a geologic cross-section that's far more professionally done, so hopefully it'll help us understand this even better. Let me get that. Okay, so here we are with this more professional cross-section. This is where we have a big thrust fault. So all the colored rocks here are the stratigraphic, the sedimentary layered rocks that were folded. And on this side, they're flanked with the colored rocks. And if we took this cross section even further back, you'd see a thicker and thicker section. And this red line here is the actual surface of the mountain today. All this lighter colored stuff. These lighter colored layers, I shouldn't call it stuff, should I? These are all layers that have been eroded away clear down to the basement. This orange color here is the basement rock, over 2 billion-year-old basement rock. So geologists, what they can do, it's fairly simple. They know all these layers over here and how thick they are. They know they went over the mountain, and they can reconstruct and know where faults go and things, and they can reconstruct it. So at one time, in theory, all this went over. Now it was being continually eroded through time, but present day, we've eroded clear down here. And this is the very highest part of the Bighorn Mountains. And we've got easily 15,000 feet of rock that's been eroded off the top, pushing 20,000 feet. So it's amazing to think about this giant structure, 35 miles across. There are much larger structures, by the way, but giant for us in our discussion. And then all this erosion that has occurred. Pretty amazing. And I want to take it just one step bigger. Let me show you another cross section that's even larger scale. So this is a cross section over a much larger scale.
Let's zoom into the map that shows the location of this cross section, which is some 275 miles long, crossing much of Wyoming, from the northeast here to the right to the southwest. The right side of the cross section starts on the Bighorn Mountains, and the left side ends on the fold and thrust belt.
So all this kind of pink color is basement rock. And this is drawn more to scale to help geologists understand the big structures. And these are the layered rocks up here, clear up here, that's been eroded. It looks kind of thin, doesn't it? That's because this is 20 miles from here to here, 20 miles, clear down to the Moho, the crust mantle boundary. And we have the Bighorns popped up. We have the Owl Creek Mountains. It's the southern part of the Bighorn Basin. So this is all the Bighorn Basin. They thrust up, high angle reverse faults, as well as the well-known Wind River Mountains. They thrust up, high angle back thrust, we call it. And then we have these here, the fold and thrust belt, a very different style of deformation of the rock. So this is the much bigger picture, much larger scale of this laramide orogeny that occurred about 65 million years ago. Well, thank you for coming along with me on this geology trip and learning more about the folding of rocks and structure and how these giant formations of rock can be tipped and eroded in the patterns that they make. And hopefully some of the things you've learned in this video, this introductory video, will help you see the world in a different way as you travel and see rock layers that are tipped on their side, or patterns that you from an airplane or your drone or something from above that are so beautiful and interesting. Thank you for watching.